In this video, we will derive an expression for the atmospheric pressure on a spherical rotating Earth due to a mixture of gases. We will take general relativity to be our theory of gravity, which, although unnecessary in this context, is of some interest in its own right. For the most part, we'll be working from first principles, so the treatment is self-contained. In addition to our expression for the pressure due to the atmosphere, along the way we will prove classical expressions for the coriolis and centrifugal accelerations in a rotating frame, the first law of thermodynamics, Dalton's law of partial pressures, and finally the ideal gas law. So to start with, we have the Earth as a ball of radius r, say. In general relativity, we know that a spherically symmetric mass distribution with a vacuum solution outside of this mass will satisfy the Einstein field equations RGAB equals 8 pi g over c to the fourth TAB. And the solution is given by Birkhoff's theorem, which says that the solution in the exterior is given by the Schwarzschild metric, which we'll write as ds squared is minus c squared into 1 minus 2gm over c squared rho minus 1 t squared minus 2gm over c squared rho minus 1 wrong place, so minus 1 d rho squared plus rho squared d omega squared, where d omega squared is the spherical metric on the unit sphere. This is all very well, but I'd like to put it into a new set of coordinates which are isotropic, so I want to write this as minus c squared a dt squared plus b times dr squared plus r squared d omega squared for some functions a and b. So we need the br squared to equal to rho squared and this quantity here to be equal to this quantity here. So we know that dr over r, taking the ratio, is equal to d rho over rho 1 minus 2 gm over c squared rho, and I want to integrate that. Okay, this will get log of r over rs for some quantity rs. This one, I'm going to make the substitution rho is equal to 2gm over c squared times cos squared theta. So this term here becomes sec squared and we have root 1 minus sec squared. Okay, d rho over rho, we don't care about the constant, so that's 2 cos theta sin theta d theta divided by cos squared theta, and this is 1 minus sec squared theta. It's 1/2, which is twice the integral. That cancels one of those. That gives a tanh, so we get sin theta over cos theta times tanh, which is sin again. It's 2 theta. So we know that theta is logarithm of root r over rs, and therefore rho is 2gm over c squared, a half into root r over rs plus root rs over r all squared, which is gm over 2c squared rs r into 1 plus rs over r all squared. Now we can take rs to be anything we like, and what I'm going to do is take rs to be gm over 2c squared. So this becomes r into 1 plus rs over r squared. And then we have that rho over r tends to 1 as r goes to infinity. So for large values of r, rho and r are essentially the same thing. Rs, you might notice, is a quarter of rho s, where rho s is 2gm over c squared, is the Schwarzschild radius. So that's where this term goes to 0 and this one blows up. Now we wanted to find A and B, so that's our next task. So we need B rho squared, d omega squared, B r squared, d omega squared. So B is rho over r all squared, which is 1 plus rs over r to the power 4. For A, that was 1 minus 2gm over c squared rho, which was 1 minus sec squared, that's tanh squared theta, which is e to the 2 theta minus 1 over e to the 2 theta plus 1 all squared. And that gives me r over rs minus 1 over r over rs plus 1 all squared for our expression for A. So ds squared is minus c squared into, let's write it this way around, t squared plus 1 plus rs over r to the 4th dx squared, where dx now, dx squared is dr squared plus r squared d omega squared. This is just your ordinary three-dimensional Euclidean space. In general relativity, a test particle can be written in terms of an energy momentum tensor like this, where rho is sharply peaked around the test particle. It would essentially be a delta function. Now, RAB minus a half RGAB, semicolon B, 0 is the Bianchi identity, or rather the contracted Bianchi identity. And this implies TAB, semicolon B, is 0. This is the conservation equation for the energy momentum tensor. So we know that UB, semicolon B, UA, plus rho UB, UA, semicolon B, is 0. I should have mentioned that U here is the fall velocity of the particle. The fall velocity satisfies UA is c squared, and in fact UA, just write it down explicitly, is equal to the derivative of the position with respect to proper time. From this equation, if I multiply by UA, I get UA times rho plus rho UB. Multiply this by UA gives UA divided by 2 semicolon B is 0, but that's minus c squared, so that derivative goes away, and that was c squared. So therefore rho ub semicolon b is 0, so we put that into here, and that implies that rho ub ua semicolon b is 0, and since rho is not 0 at the location of the particle, we have this equation here, which is just the geodesic equation. So the motion of the particle, of test particle, is given by the geodesics in the space-time. To work out the geodesics, we use a Lagrangian. Consider the Lagrangian as c squared a into t prime squared minus bx prime squared, where primed represents differentiation with respect to proper time. What I'd like to do is form a Hamiltonian, because I'm going to need that later, and I'd like to replace the proper time with the coordinate time and have a variational principle, essentially derive a Hamiltonian from that. So to do this, I work out the t prime equation, which is dl by dt prime. There's no explicit dependence on time in this Lagrangian, so that thing is a constant, which will tell me that a t primed is some constant mu. What I can't do is substitute t primed into this equation, because that would not give me an equivalent set of equations. What I need to do is construct a new Lagrangian, L being the old Lagrangian, and since I'm not in future going to be differentiating with respect to t primed, I'm going to impose that a t primed is a constant by using a Lagrangian multiplier, lambda. Okay, we can differentiate this with respect to t primed, and we want that to be equal to 0. So we'll get c squared to a t prime minus lambda a is 0. Which implies that lambda is equal to 2c squared, and therefore L is minus c squared a t prime squared minus bx prime squared. That's t prime squared c squared a plus bx dot squared, where dot now represents differentiation with respect to coordinate time. Putting the value for t primed in from here, that's going to be proportional to, I'll drop the minus sign because I'm only interested in proportionality and factor of mean there. So it's proportional to b over a squared x dot squared plus 1 over a. So this is our new Hamiltonian. We should perhaps check that this gives the same equations of motion as the original Lagrangian. So the original Lagrangian gives me dl by dx prime prime is dl by dx. I think I've been calling this capital X. So from here we're going to get 2bx primed is equal to gradient of b x prime squared minus c squared gradient of a t prime squared. What do we get from this Lagrangian here? dl by dx dot, you can't see the dot there, is dl by dx. That is 2b over a squared x dot dot is gradient of b x dot squared over a squared minus 2b gradient of a over a cubed x dot squared minus gradient of a over a cubed. Now x dot is x primed over t primed, and t primed is mu over a. So we have that relationship. So this tells me that 2b over a squared times an a, so that's, I think, x primed with a 1 over a down there is equal to grad b x prime squared if I put this one on, no, actually that should be up there, minus 2b grad a over a x prime squared minus grad a over a times t prime squared. I've divided it through by u squared in this equation. On this side we have 2bx primed, that's differentiating that top, differentiating the bottom we're going to get plus 2b grad a x prime squared over a squared times a, and there's going to be a minus sign in there, is equal to grad b. Those cancel out, and this equation, if everything has gone right, should be equivalent to this equation up here. That's correct. I had an a when I differentiated, oh, that should have been a squared. So we don't have that. Which shows that the two Lagrangians give the same set of equations. Next, we're going to rescale the Lagrangian again because I want to convert it to Hamiltonian in due course. So this was e over a squared x dot squared plus c squared into 1 over a, minus 1 here in that case. Actually, going back to this set here, I noticed that I missed out a c squared here, c squared here, c squared here, and a c squared here. So this is what we get as an equivalence Lagrangian. This term is just a constant that's going to be useful later on. we're going to take the limit c goes to infinity, and this will then have a nice, well-defined limit. Let's go to a rotating frame, in which case, as the Earth rotates around its axis, if you are at a point rotating with the Earth, you see that the position in the inertial frame has a time derivative which is little x plus omega cross x, where little x are the coordinates you measure with respect to your point on the Earth. So L is m over 2 b over a squared x dot plus omega cross x all squared plus c squared into 1 over a minus 1. At this point, let us construct a Hamiltonian. So we write P as dl by d little x dot, which is mb over a squared x dot plus omega cross x, or in other words, x dot is a squared p over m b minus omega cross x. The Hamiltonian is a function of x and p, and it's given by x dot p minus L. It's just a Legendre transformation. Well, I'm going to be a bit sneaky here. I'm going to write this expression out in powers of x dot, and then notice that the Hamiltonian is given by preserving the x dot squared terms, so I get mb over 2a squared x dot squared. The terms which are linear in x dot all disappear, and the constant terms change sign. So we get this thing squared, so we get mb over 2a squared omega cross x all squared. And that's changed sign, and also this has changed sign. But we can't leave it like this. It has to be written in terms of this quantity here. So that gives me mb over 2a squared into a squared p over mb minus omega cross x all squared minus mb over 2a squared omega cross x all squared minus c squared into 1 over a minus 1. So this gives me a squared p over 2mb p squared from that, minus that times that. It gives me an m p dot omega cross x, or if I prefer, I can swap the dot and cross around, so I'll do that. This term squared is going to cancel out with this, minus c squared into 1 over a minus 1. At this point what we'll do is take the limit as c goes to infinity. So let's have a quick look at b, which, if you recall, is 1 plus rs over r to the 4. 1 plus gm over 2c squared r. 4, and that goes to 1 as c goes to infinity. What about c squared 1 over a minus 1? That's c squared into, now this gives me 1 plus rs over r squared over 1 minus rs over r squared minus 1. You can use the binomial theorem on that. C squared into 1 plus 4 rs over r plus order rs over r squared minus 1. And that's equal to 4 gm over c squared 2 c squared r times c squared plus order 1 over c squared terms, and that tends to 4 gm over 2 gm over r. So there should be an m over 2 multiplying this term here as well. The over 2 there. So what is the limit of the Hamiltonian in this case? Well, h of x and p would go to p squared over 2 m minus mp cross omega dot x minus gmm over r. Let me just make a correction. There's no p there. Let us see what the equations of motion are in this case. So Hamilton's equations are that x dot is dh by dp, and that can be p over m minus m omega cross x. I can swap the dot and cross back over. Or in other words, p is m x dot plus omega cross x, which is actually what we knew from the Lagrangian. P dot is minus dh by dx, is minus mp cross omega minus plus gm m over mod x cubed times, here r is mod x. So p dot is mx double dot plus m omega cross x dot, and that's equal to m times mx dot plus m omega cross x cross omega. I don't like the number of that m shouldn't be there. So this is the m missing here. That looks good. That shouldn't be there. Let's have another think about this. Yes, that shouldn't be there. Good. So mx double dot is equal to minus 2m omega cross x dot, that's that term, and that term there. Swap the order of the cross product, express a minus sign. There's no m there anymore, I got rid of that. Minus m omega cross x. Oh, and I forgot to include this term here, minus gmmx over mod x cubed. So what do we have here? We have the effective force is given by coriolis term. This term here is the centrifugal, and this is the gravitational. So this is exactly what we would expect. So far, everything is working. Our next piece of work is to move this into statistical physics. So the first thing we're going to do is need to know density of states. In expressions to come, we'll often have the sum over I, where I is states, the mechanical states. We will want to replace the sum by an integral. So the sum of Fi will be the density of states times the integral of a suitable function f times d3p d3x. It's an integral in phase space. We need to know what this density is. So we consider a very small box of side length L and try and solve Schrodinger's equation, in this case without a potential, minus h bar squared del squared psi over 2n. Right, I want to solve this. So what we'll do is we'll impose periodic boundary conditions on the surfaces. So we write psi as x of x, y of y, z of z. In other words, we use separation of variables. This equation becomes x double prime over x, prime over y, plus z double prime over z is equal to minus 2me over h bar squared, which is constant. So therefore, I can rearrange this equation. X double primed over x is equal to some constant minus y double primed over y minus z double primed over z. This thing is a function only of x, and this side is a function only of y and z. So this is independent of x, but it's equal to f of x. So this thing is independent of x, so that must be constant. So that thing plus k1 squared x is 0, and similarly we have these things. Well, these have solutions. Psi is e to the I k dot x. Now we want to impose periodic boundary conditions, which implies that e to the I k x plus L is k1 is e to the I k1 x. So in other words, k1 L is 2 pi n for some n, let's call it n1 in z. Now p, the momentum, is minus I h bar times the gradient. So p of psi is h bar k psi. The states we've found here are momentum eigenstates with this value of the momentum. And we know that k, vector k, is in 2 pi over L vector n, where n is in z cubed. So h bar times that is that, and that's h over L n, where h is Planck's constant, h bar is a reduced Planck's constant. This shows that one state occupies a volume in p space, momentum space, of L cubed over h cubed. Now taking L to be very small, so L cubed goes to dv, this shows that the density of states, sorry, that's up the wrong way, h cubed over L cubed. The density of states is the reciprocal of this, that is dv over h cubed. If it were the case that we had extra degeneracy due to, say, the spin of the particle, then we have to multiply by the spin degeneracy. So we did it for a very simple scalar particle with no internal degrees of freedom, such as spin. So that's our expression for the density of states. So the sum over I of Fi goes to gs over h cubed, the integral d3x, integral d3p of f. That's our way of translating between the sum over states to an integral. Right, now consider a collection of particles. n particles, total energy E. Energy is conserved. This is a consequence of Noether's theorem and the time translation symmetry of the system. So if there are states labelled 1, 2, 3 and so on up to however many you like, the number of ways of arranging indistinguishable particles in this this is rather important, distinguishable particles in a state given by the multinomial coefficient n factorial, n1 factorial up to n2 factorial and so on. We want to maximise this quantity subject to the constraints that the total number of particles is preserved and is the total energy. So that's equivalent to maximising log omega subject to the total number of particles being constant and total energy being constant. So these alpha and beta are Lagrange multipliers. Now, log of n factorial is approximately, actually it's exactly the sum 1 up to n of log n, and that's approximately the integral 0 to n of log x dx when n is very large, and that's n log n minus n, and the derivative with respect to n of log n factorial is approximately log n factorial minus log n minus 1 factorial is log n, which also we get from differentiating that. So let's try and work out what collection of ni I need in order to maximise or extremise f. So the partial derivative with respect to ni is 0. Let's write that out using this thing here. That's log n minus the sum log ni factorial there, minus alpha the sum of ni, minus beta the sum ni ei. So that term gives me log n times dn I dni, but that's just 1 because n is the sum of the ni, minus alpha minus beta ei. Oh, and I've forgotten this term here, minus log ni. Okay, well I can rearrange that and give ni over n is e to the minus alpha minus beta ei. We call that pi. That's the probability that a particular particle is in the state I. Now we know that the sum of the probabilities is 1, or equivalently the sum of the ni is n. So we get 1 is equal to e to the minus alpha times the sum of e to the minus beta ei. Well, let's call z1 the sum e to the minus beta ei. This is the one particle partition function. And so we have pi is e to the minus beta ei divided by z1. Now let's see what would happen if we have many particles, but we've worked out what happens for a single particle. If we have many particles, then the partition function would be the sum of e to the minus beta ei for e1 ei1 plus e2 i2 plus dot 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 plus eik k i1 i2 up to ik. And that's just z1 times z2 up to zk. So if we have n particles, and suppose they're all identical, so each of these different possibilities for the energy are all the same collection, you get the total partition function is z1 to the n. Right, let us construct the entropy for such a system. So the entropy S is equal to k times log omega. K log n factorial minus the sum of log ni factorial, n log n at this approximation, minus the sum of ni log ni. Remember, ni is equal to pin, and the sum of the ni is equal to capital N. So that term there cancels with that term, and that gives me minus kn sum pi log pi. It's minus kn sum pi. Now remember, pi was e to the minus beta ei over z1. So that gives me minus beta ei minus log z1, and that gives me k beta, the n times, that is an niei, plus k n log z1, the sum of the pi's is 1. K beta, that's the total energy, plus kn log z1. Or if I rearrange this, I get E is S over K beta minus N over beta log z1. What we'll do next is take the differential of this equation. So dE is ds over k beta plus d beta terms into minus s over k beta squared plus n over beta squared log z1 minus n over beta d by d beta log z1. We should regard z1 as a function of beta, but it's also a function of the volume, because the energy levels depend on the volume too, so that's a constant volume. We have minus n over beta d log z1 by dv, that constant beta, dv, and finally minus log z1 over beta dn. Well, let's try and work out this thing. So minus n over beta d by d beta, constant volume, log z1 and z1 was the sum of e to the minus beta ei. And that gives me a minus ei and then a pi z1. Z1's cancel. And that gives me the sum of ei ni over beta, total energy over beta. So we have this term here is the total energy over beta plus n over beta squared log z1 minus 1 over k beta squared times s, which was k beta e plus k n log z1. K's cancel, beta squared. So that exactly cancels with that. So 1 over beta e, that cancels with that, so that's 0. So all of that term goes away. So we have dE is T ds minus P dV plus mu dN. Where we set T to be 1 over K beta. P is going to be N over beta d log Z1 by dV, a constant beta, which is the same thing as d log Z by d beta by dV, a constant beta, times K T. Call it T. Now T is the temperature. We recognise this as the first law of thermodynamics. From this expression, if we were to take, say, a box of height h and allow the box to move by an amount dh, so dv is dh times a, where a is the cross-sectional area. The amount of work the gas does on this is given by the force times the distance travelled, which is dh. So that's equal to dE, and the amount of work this is minus P dV. Now, we're interested in the energy of the gas. So actually this is the amount of work the gas does, so this is the amount of energy the gas loses, so we really want a minus sign there. And that's equal to minus PA dH. So we find that the pressure, P, is F over A, corresponding to our usual notion. And the pressure we're talking about is the pressure on this particular surface here. Right, next, suppose we have several gases all mixed together. Z, the total partition function, is Z1 to Zk, and therefore log Z is the sum of the logarithms of the Z's, and thus the pressure, total pressure, is the sum of Kt d by dV, that constant beta of log Za. This is the sum of the P's. In other words, the total pressure is the sum of the partial pressures, and this is Dalton's law of partial pressures. Right, let us return to the atmosphere. We can write the Hamiltonian from earlier in the form 1 over 2mp minus m omega cross x all squared plus v of x, where v of x is minus m over 2 mod omega cross x squared minus g mm over mod x. There's the Earth. The angular velocity points directly through the North Pole. The magnitude, I just write as little omega, which is 2 pi radians per day. If we're at latitude lambda, then by considering this triangle, there's omega. That angle there is the latitude, so that angle is the latitude. We'll take a basis, so that will be EZ, that will be E north, and orthogonal to this we'll have E east. So you find out that east, north, EZ is right-handed. Basis. So you have east, north and vertically upwards. Therefore omega, that's in the EZ direction, that's in the E north direction. There's no component in the easterly direction. In the northerly direction we get the cosine, sine lambda, multiplied by square omega. We're going to consider a column of gas of cross-sectional area A, which is very small and centred at the origin. Let's just say x equals y equals 0. So we know that we can make this approximation throughout all points in the column. So essentially x here is just 0, 0, z. And therefore omega cross x is omega 0 cos lambda sine lambda cross with 0, 0, z. That's equal to omega z cos lambda. This term gives me, next I'm giving that times that minus that times that, that's 0. And finally the last term, where 0 has got to be orthogonal to that, so the modulus of omega cross x squared is omega squared z squared cos squared lambda. So that helps me write this thing down. Okay, so v of x is actually just a function of the z coordinate. It's minus a half m omega squared z squared cos squared lambda minus g m m over mod z. We assume that z is greater than 0 because z is measured from the centre of the Earth. Right, let's work out the one particle partition function. So we have gs over h cubed because we're replacing the sum by an integral. Have the integral dx dy over the cross-sectional area of the column. We'll have the integral dz, vertical height. We'll go from height r to z, arc the surface of the Earth. In most cases that's what we'll take it to be. We'll have e to the minus p minus m omega cross x squared over 2mk t d3p, and let's not forget this term here. I've already got the dz. Well, I can shift p by this constant, because it is constant in this integral here. I should perhaps write an integral sign. in there, and then I can do it. So I end up with gs over h cubed. Doing that gives me a 2 pi k t m 3 over 2, at which stage nothing depends on x and y, so that just gives me the area integral r to z e to the minus v of z over kt dz. Next, compute the total number of particles. Let's suppose the total number of particles in the column of air or gas is n0. Then essentially the same sort of argument, the same sort of integral shows you that the number at height z, that's given by the sum of all of the ni's for a state such that ngi is less than the maximum ng available at height z. In other words, this gives me the integral r to z e to the minus v of z over kt dz times n0 divided by the integral r up to L, where L is the maximum height of the column. So that's what we get. Log Z1 is log GSA over h cubed 2 pi kt m to 3 over 2 plus log integral r to z e to the minus v of z over kt dz. So pressure at height z is kt d by dv at constant temperature, let's put an n there, times log z1. This thing doesn't depend on the volume. Actually, the volume is just changing dv. In this case, it's just changing dz times a. Okay, so this is actually nk over ta d by dz of log z1. So that term's irrelevant, and we just end up with nkt over a e to the minus v of z over kt divided by the integral r to z e to the minus v of z over kt dz. Put in the expression for n in this case. That gives me n0 kt over a e to the minus v of z over kt divided by the integral r up to L now, e to the minus v of z over kt dz. Now v of z was minus a half m omega squared z squared cos squared lambda minus g m m over z. Let's have a look at v of r plus h minus v of r. Minus a half m omega squared h squared plus 2rh cos squared lambda minus g m m over r plus h plus g m m over r. And let's linearize this. So that's h into m omega squared, so minus sine r cos squared lambda. From here we're going to get plus g m m over r squared plus plus big O h squared. Now going back to this equation here, I can multiply by e to the v of r over kt, e to the v over r over kt, top and bottom, if I want. Makes no difference. This thing I'm going to write as little g because it's the acceleration due to gravity at the surface of the Earth. So p at height z is then n0 over k t over a e to the minus m, there should be m in there, mg over mgz over kt divided by the integral from r to infinity, that times e to the, going actually now from 0 to infinity of e to the minus mgz over kt dz. And that's equal to n0 kt over a e to the minus mgz over kt divided by 1 minus e, actually if that was L, mgl over kt, and I've got to multiply by an mg kt. That gives me that expression. In the limit that L goes to infinity, we get P of z is mg n0 over a e to the minus mgz over kt. There's this thing, so if we have a mixture of gases, we have, by Dalton's law, the pressure at height z is the sum ma g n a over the area e to the minus mg, that's ma g over k t, and that's the formula for atmospheric pressure. Note it is a maximum entropy state for the system, so if you were to think that the particles may fly off into space, the vacuum of space, that would be a lower entropy state, so it would violate the second law of thermodynamics. Now another thing we can do with this formula here is see what happens if we assume that L is actually, if L is small, so we're actually considering, say, a sealed container containing a gas, in which case I can replace the exponential by the first term as it's serious. So I'm looking at the limit mgl over kt goes to 0. Then the pressure at height z, well, z would be between 0 and L, so mgz over kt also goes to 0, so you have mg n0 over a, and this thing, you can use the first term in the, well, the first two terms in the Taylor series, or you can use L'Hopital's rule, that works just as well. mgl over kt. So the mg's cancel off. That's n0 kt over al. But what is al? That's just the volume. So we have PV is n0 kt, and that's the ideal gas law. For heavy gases, then this approximation is no longer true, in which case you have to use something like this. This would be particularly true if you were using something like sulfur hexafluoride. In the case of sulfur hexafluoride, you could take an open container, and if you started filling it with gas, it would essentially just sit there rather like a fluid does, any other fluid. So